Hello, my name is John Cody. This is part 3 in a series of videos on the scattering amplitudes and Platonic mathematical structures. This is based on a talk given by Nima Arkhani Hamed from the Institute of Advanced Study at the Amplitudes 2022 conference. So Nima gave a talk there. He was talking about scattering amplitudes and geometric shapes. So in part 1 of this video series, I gave a summary of what Nima was looking for. So in his part 1, I did a recap and said that Nima is looking for a certain kind of mathematical structure in the Platonic world of ideas that have certain properties, and we saw that the mathematics of Universal Hyperbolic Geometry also has these properties that he's looking for. So in part 1 of the talk, he's talking about scattering process of particle scattering in physics. So you have a particle trajectory, a four momentum p given by the energy and momentum of the particle, and it satisfies the Einstein relation. P squared is equal to E squared minus P squared, and that's equal to M squared, and that's called an on-shell condition. It's when the four momentum is on the mass shell. So here we have 2-to-2 scattering, 2 particles in, 2 particles out, and we have a propagator in the middle, P, which is given by a subset of the momenta. So in this case, it's P1 minus P2. So this propagator is a virtual particle, and that means it's off shell. So we have the propagator 1 over P squared minus M squared, where this P squared minus M squared is not 0, and that's called a virtual particle. And he goes on to say in particle scattering, when you have 2 particles in, this is a scattering process, 2 particles in, 2 particles out, and this is one of the diagrams that results. So you have 2 particles in, it creates a virtual particle, and that virtual particle propagates a certain distance in space-time and then decays into two other particles. And he also goes on to say that this can be represented by a geometric shape where you have 4 points, P1, P2, P3, P4, that represent the 4 momentum, and we have a point on the interior of the shape, and when this representing the virtual particle M, so this P1 is this one here, P2 is this line here, P3 is this line here, and P4 is this line here. And when the virtual particle goes on shell, we have what's called a resonance condition, when a subset of the momenta P1 plus P2 squared is equal to M squared. Then the amplitude, the scattering amplitude, we see that we get a pole in the denominator here. So we get a pole when the virtual particle becomes real. And quantum mechanics tells us that the amplitude, when we have a pole, that the amplitude factorizes into 2 smaller amplitudes. So it has this factorization property where the 2 particles come in, generate an intermediate particle, and multiply that intermediate particle decays into 2 other particles. So this pi squared is equal to m squared. So the rules of space-time and quantum mechanics reflected in the scattering process are that locality means that we only get poles when a subset of the momenta go on shell, and quantum mechanics, or unitarity, says that we get this factorization property. So here's a scattering process where a subset of the momenta P1, P2 plus P3 goes on shell. So we have P squared minus M squared is on shell, is on the mass shell, so it's 0, and then we also, we see that it factorizes we see this factorization into two smaller or lower point amplitudes. So he said that he wants to find a different question directly in kinematic space, to which A, the amplitude is the answer. A is a function of the momenta, momenta of the particles, without referring to space-time and quantum mechanics, but which nonetheless give correct poles and correct factorization. Again, he's saying that the rules of space-time and quantum mechanics are reflected in this scattering process, where locality, the poles go on shell, unitarity is the factorization, and we get a pole when the intermediate particle goes on shell, when it goes to the boundary. So what he's saying is, what he's after is, he's looking for the kinds of mathematical structures in the Platonic world of ideas that have this property that there are a set of objects that are indexed by n, that is going to be the number of particles, and it needs to have this property that when you go to the boundary of this object, the boundary factorizes into the product of other objects of the same type that you have seen before. And that should be a feature of the geometry. So he says, if we find these interesting geometric structures that have this self-factorizing property on their boundaries, then we're close. We have an opportunity to look for some way to ask a question of that structure whose answer we'll interpret as the amplitude that depends on a bunch of momenta. But this basic fundamental fact about the factorization of the structure will turn into factorization of the amplitudes. In that way, locality and unitarity will be outputs out of this object rather than inputs that went into it. And that is roughly the kind of things that he is after. So in part 2, we looked at it from the point of view of mathematical framework of rational trigonometry and universal hyperbolic geometry, which takes the point of view that geometry is really about formulas. So we'll summarize the results that we saw in part 2 of the video series. So we have the scattering process. We have this depicted here. This is one of the Feynman diagrams. Two particles in generates a virtual particle, and then the virtual particle decays into two other particles. So it's 2 to 2 scattering, and that's depicted by this shape here. P1, P2, P3, P4 are the 4 momenta of the scattering process, and M is the virtual particle. And over here on the right, we have a representation from Universal Hyperbolic Geometry of this shape here with the particle, fourth particle in the interior. So the points A1, A2, A3, and A4 are projective points in universal hyperbolic geometry. And we have this shape here. It's a quadrangle formed by A1, A2, A3, and A4. And this is a general triangulation of that shape. So I explained what these quantities were in the last video, but I'll go over it again. We have quadrants Q1, Q2, Q3, and Q4. We have spreads at A1 of R1 and T1, R2 and T2 at A2, R3 and T3 at A3, and R4 and T4 at A4. And also spreads there's a spread S1 at A1, spread S2 at A2, a spread S3 at A3, and a spread S4 at A4. We also have a point on the interior, in general position on the interior, which triangulates the shape like this. And it has spreads U1, U2, U3, and U4. and also there's the quadrants between A1 and A5 is P1, the quadrants between A2 and A5 is P2, the quadrants between A3 and A5 is P3, and the quadrants between A4 and A5 is P4. And the main result we achieve, the main formula from this triangulation of the projective quadrangle was this equation here. It's a quadratic equation, and what we're seeing here, we have this projectively invariant quantity called A, the quadri of a projective quadrangle, and on the right-hand side here we have we came up with this formula for the right-hand side of the. This is an alternate form of the equation for the quadri of a projective quadrangle, and you see that it's a quadratic equation. So here in the numerator we had 64 times u1 times u2 times u3 times u4, that's the spreads here, is times p2 squared times p4 squared times 1 minus s1 squared times 1 minus s3 squared, all divided by r1 plus t1 minus s1 squared times r3 plus t3 minus s3 squared. So what we have here is on the right hand side that we get a pole when this point A5 goes to a boundary. Let's say it goes to the boundary between A1 and A2 on the line. The line is the join between A1 and A2. When it gets to this boundary, then this spread U1 goes to 0 when this point is on this line, and the spread T1 goes to 0 also when this point is on the line. So what happens is we get a pole in the denominator here, because R1, when T1 goes to 0, we have R1 is equal to S1, and that's going to become 0. And so this is a double pole in the denominator. And in the numerator, U1 is going to be 0 when this point A5 is on this boundary. So U1 becomes 0. So we have this 0 canceling one of these poles. We had a double pole here, leaving a single pole in the denominator. So this U1 is called a multiplication kernel, and it makes the pole structure work out for scattering amplitudes. So the same thing happens when the point A5 goes to the boundary here of the quadrangle. So it's A2, A3 boundary. When it hits that boundary, then U2, the spread U2 is 0, and at this point here we have R3 goes to 0, the spread R3 goes to 0, so that's in this equation. R3 is 0, and we get T3 minus S3 is 0. T3 is the same as S. When R3 goes to 0, then T3 is equal to S3, and we get a pole right here. It's a double pole again, and that's one of the zeros here. U2 was 0, so that cancels one of the poles, and we get a single pole in the denominator. Same thing happens when you go to the boundary on the line formed by A3 and A4. So when this point U5 is on this line, then U3 is 0, and then T3 is 0. T3, the spread here becomes 0, and then R3 is equal to S3, and that generates a double pole in the denominator, and it gets canceled with one of the U3s. It gets canceled by the 0 U3 when this line, the U3 is 0 when A5 is on this line. And the same thing happens again when the point A5 goes to this boundary down here. Then we have U4 is 0 and R1 is 0. So in this equation here, the U4 is 0, and then R1 is 0, and we get T1 is equal to S1. So T1 minus S1 is 0, and that's a double pole. It's canceled by 1 and 0, so we get a single pole in the denominator. So that shows that we get a single pole in the denominator when the point goes to any of the boundaries of the quadrangle or quadrilateral shape. And then these U1, U2, U3, U4 are like a multiplication kernel. And then so that's the locality structure that he's looking for. And the unitarity structure is the factorization into two pieces. So we see the remainder here easily factorizes into two pieces. So it could be like P1 or P2 times P4, one of each of those times 1 minus S1 squared. That could be one factor, and the other factor could be P2 times P4 times 1 minus S3 squared. So we get this locality and unitarity structure that he is looking for in the algebraic structure here in universal hyperbolic geometry from the equation of the quadri of the projective quadrangle. Thanks for listening. I will provide links to the other videos, part 1 and part 2, as well as Nima's talk.